Hello, today we want to talk about the AMGM inequality with rational weights. So the inequality says the following. We have a1 to the power of p1. These are our rationals times a2 to the power of 2, and so forth till an to the power of pn. And this is smaller or equal to p1 times a1 till pn times an. So we condition on these pi's the following. First, of course, that they are non-negative. Second is that they are all in the rational numbers, and that they all sum up to 1. Okay, so let's prove it. The proof is kind of in the condition. So if we say that pi's have to be in the rational numbers, then we can always find an m in the integers such that we can rewrite the pi's as a quotient of two integers, ki divided by m, where these ki's are also in the integers. And this m is then the common denominator of all of these rationals. We can find such a quotient always. Now, why did we do that? If these pi's sum up to 1, then if we use this new form of these pi's, then we can write ki divided by m. This is equal to 1. Well, and this is a constant, so we can drag it out of the sum. And if you multiply it out, then we have the summation of all of these ki's from 1 to n equals m. Now, recall that what the AMGM inequality is saying, which is we can take b1 to bm. Let's say for example, let's use the this number to the power of 1 over m. That's smaller or equal to 1 over m b1 plus, so all of these numbers summed up. Okay, this is the AMGM, the original AMGM inequality. Now let's write our left-hand side of the inequality, a1 to the power of, oops, that's not it yet, to the power of a1 times a2 to the power of p2 times an to the power of pn. Well, and we want to rewrite these p's. So this is a1 to the power of k1 divided by m times a2 to the power of k2 to the power of m, which is not yet, that's not it, an to the power of kn divided by m. Now, the next step is to extract this 1 over m out. So we have a1 to the power of k1 till an to the power of kn to the power of 1 over m. So if we look closely enough on this on what is written inside of this bracket, we see that we have m factors here, because if we add up all of the exponentials, they add up to m. So we have m factors, and we can use the AMGM inequality for that. But let's write it out in a bit more explicit way. So let's write out a1. This a1 to the power of k1, we write it out as like explicit multiplication, and then an as well. I mean, for all of these factors, of course. So what do we see now? We see this here is, of course, k1 times. And this here is kn times, and for the other ones as well. So, and then ultimately for all of them together, we have to have like k1, like the summation of all of these ki's times. And of course, that's just m. We know this from this inequality that I just marked with a red star. Okay, so we could think of the first one as like b1, this second one as like b2, and so forth until we get to this one. That will be our b big M1. Okay, so this is smaller or equal to 1 over m, and then we sum them all up. all of these m factors. Okay, this is just k1 times. This here is kn times. Of course, if we sum them up a certain, like if we sum them up k1 ki times, then we can just multiply them out, multiply that factor. We can write here k1 times a1 till we get to kn times an. So now we distribute the 1 over m for all of these summands, and then we have k1 divided by m times a1 to kn divided by m times an. Now, we know from above, we have established this already, that's just p1, and that is pn. So we have p1 times a1 till pn times n, thus finishing our proof with the right-hand side. And that's it.